Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient canyons of Mars, where blue stones hold secrets from a world that once knew flowing water. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On a day when Earth's winds carry autumn leaves and the familiar scent of changing seasons, a six-wheeled rover moves silently across the rust-colored plains of Mars. Perseverance rolls forward at the speed of a cautious beetle, its cameras sweeping across terrain that has known no footsteps for 4 billion years. The Martian morning arrives cold and thin, its salmon-pink sky holding barely enough atmosphere to stir the finest dust grains. Each wheel turn leaves temporary impressions in soil that will remain undisturbed until the next dust storm arrives to erase all evidence of passage. The rover approaches what mission scientists have labeled simply as Canyon Site Alpha, an unnamed depression carved into ancient bedrock where something unusual waits in the shadowed walls. Here, where the morning sun angles low across fractured stone, geological layers reveal themselves like pages in a book written by water and time. Each stratum tells of different epochs, different climates, different possibilities for a planet that once held rivers beneath a thicker sky. The canyon walls rise roughly 15 meters above the rover's position, their surfaces showing the familiar patterns of erosion and deposition that speak of flowing liquids and gradual accumulation. Perseverance extends its robotic arm with mechanical precision, positioning the Pixel instrument close to an outcrop that gleams with an unexpected color. Not the familiar iron red of Martian dust that has painted this world for billions of years, but something rarer, patches of deep blue-green that catch the pale sunlight like scattered gemstones embedded in stone. The spectroscopic analysis begins immediately. Invisible laser pulses reading the chemical signature of minerals that formed when this canyon knew the sound of running water. Each pulse lasts mere nanoseconds, yet reveals information about processes that unfolded across millennia. The rover's various instruments work in concert, like a symphony of scientific inquiry played out in the Martian silence. Mastercam Z captures high-resolution color images, while Supercam provides elemental analysis from a distance. The RIMFAX ground-penetrating radar peers beneath the surface, mapping subsurface structures that might reveal the extent of these unusual formations. Each measurement adds another piece to a puzzle that began forming when Mars was young and water flowed freely across its surface. The initial data streams back to Earth across 140 million miles of space, a journey that takes between 4 and 24 minutes, depending on the orbital positions of both planets. The signals arrive at massive radio telescopes scattered across Earth's surface, then travel through fiber optic networks to the Jet Propulsion Laboratory, where teams of geologists and astrobiologists gather around monitors displaying wavelength graphs and elemental compositions. What they observe defies the typical Martian palette, challenging assumptions about the planet's chemical evolution and water history. These are hydrated sulfate minerals, copper-bearing formations that speak of groundwater seepage and chemical precipitation processes that require not just liquid water, but stable liquid water, present for thousands of years. The spectral signatures match those of minerals found in Earth's most arid regions, yet with subtle differences that hint at formation under conditions that existed nowhere else in the solar system. The copper content gives these formations their distinctive blue-green coloration, a hue that would have been invisible beneath the reddish dust that now blankets most of Mars. It only took 3 billion years for Mars to forget how to rain, though the planet still remembers in ways both obvious and subtle. The blue-green crystals embedded in the canyon wall represent a kind of planetary memory, each mineral grain a witness to humidity and flow, to underground rivers that move through porous rock carrying dissolved metals toward the surface. The rover's instruments detect magnesium, sulfur, and traces of copper elements that once danced together in ancient Martian springs before settling into these crystalline arrangements that now glimmer like forgotten jewelry. The precision required to detect these formations represents decades of technological advancement. Earlier, Mars missions might have passed by these deposits without recognition, lacking the sophisticated instruments needed to identify their unique chemical signatures. Only took 40 years of planetary exploration to develop eyes sensitive enough to see Mars as it truly was, rather than as it appears through the filter of accumulated dust and oxidation. The irony of discovery often lies in developing the right questions before the universe reveals its answers. There remains something mysterious about the precise formation mechanism, a puzzle that keeps planetary scientists returning to their data again and again. While Earth's desert regions produce similar evaporate minerals in dry lakes and salt flats, the Martian varieties show subtle differences in their internal structure, hints of environmental conditions that existed nowhere else in the solar system. Perhaps the lower gravity influenced crystal growth rates, allowing formations to develop in patterns impossible under Earth's stronger gravitational field. Or the different atmospheric composition affected how water molecules arranged themselves as they transitioned from liquid to solid preservation. The atmospheric pressure on ancient Mars remains one of geology's most debated topics. These mineral formations suggest pressures high enough to maintain liquid water at the surface, yet other geological evidence points to a thin atmosphere even in Mars's early history. The copper-bearing sulfates might hold clues to resolving this paradox, their chemistry preserving information about the partial pressure of water vapor and carbon dioxide in the ancient Martian atmosphere. The canyon holds its secrets quietly, as it has for eons beyond human counting, its silence broken only by the occasional whisper of wind carrying dust across its rim. Perseverance photographs the formations from multiple angles, documenting their context within the broader geological setting. These images will be studied for decades, each pixel containing information about a world that once exhaled water vapor into morning mists, where underground aquifers sustained chemical reactions that Earth's geologists are only beginning to understand. The rover's memory banks fill with data that will outlive the mission itself, preserved for future generations of scientists who will bring new techniques and perspectives to these ancient mysteries. Only took 50 years of space exploration to realize that finding life on Mars might be less important than understanding how planets die. The blue stones wait patiently in their canyon wall, holding their chemical secrets with the same patience that stone has always shown, indifferent to the mechanical visitor that has come to read their story after so many ages of silence. They represent both an ending and a beginning, the end of Mars' active hydrological cycle, and the beginning of human understanding of planetary evolution on a scale that dwarfs all earthly experience. The canyon stretches before Perseverance like a wound in the planet's memory, its walls carved by waters that flowed when the solar system was half its current age. Ancient riverbeds snake through the depression, their meandering patterns still visible despite billions of years of wind erosion and dust accumulation. These channels follow the gravitational logic that all water obeys, seeking the lowest path through resistant bedrock with the patient persistence that only geological time allows. The rover's ground-penetrating radar reveals subsurface structures that extend far beyond what visible light can detect. Buried channels run parallel to the surface expressions, suggesting that this canyon system once supported both surface streams and underground aquifers. The radar signatures show distinct layers of sedimentary rock interspersed with what appear to be paleo-channel deposits, ancient river gravels now cemented into stone. Each layer represents a different phase in Mars's hydrological evolution, from vigorous flowing streams to intermittent seasonal flows to the final desiccation that left only mineral traces. Mastcam Z captures the subtle color variations in the canyon walls, revealing stratification that speaks of cyclical deposition over enormous spans of time. Dark layers alternate with lighter ones, suggesting periods of different water chemistry or seasonal variations in sediment load. The camera's filters can distinguish between iron oxides, sulfate minerals, and clay deposits, each representing different environmental conditions during the canyon's active period. Some layers show the characteristic red coloration of oxidized iron, while others maintain the gray-green hues of minerals that formed in reducing environments where oxygen was scarce. The mathematical precision of water's erosional patterns remains constant across planetary boundaries. On Earth, meandering rivers follow predictable curves determined by flow velocity, sediment load, and channel width relationships that geomorphologists have quantified through decades of fieldwork. The Martian channels display these same geometric relationships, their sinuosity ratios and wavelength-to-width ratios falling within ranges typical of terrestrial rivers. Only took 1 billion years for Mars to demonstrate that fluid dynamics operates the same way regardless of atmospheric pressure or gravitational field strength. Mission scientists compare the canyon's dimensions to similar features on Earth, finding striking parallels with rivers in the southwestern United States. The channel width suggests discharge rates comparable to the Colorado River during moderate flood stages, implying substantial water volumes moving through this system during Mars' active period. Yet the preservation of fine-scale features indicates that these flows occurred episodically rather than continuously, with long periods of quiescence allowing delicate mineral formations to develop undisturbed. The irony of studying ancient Martian rivers lies in their superior preservation compared to Earth's geological record. Terrestrial rivers constantly modify their channels, erasing evidence of earlier flow patterns through ongoing erosion and deposition. Mars's channels remain frozen in time, their last configuration preserved like a photograph of the planet's final hydrological breath. Only took the death of an entire planetary water cycle to create the perfect museum of fluvial processes. Spectroscopic analysis of the channel floors reveals mineral assemblages that require prolonged contact with flowing water. Phyllosilicate clays line some sections, their crystal structures indicating formation through chemical weathering of volcanic rocks under alkaline conditions. These clays could only have formed through sustained water-rock interaction over timescales measured in thousands of years. The presence of smectite minerals suggests fluctuating wet-dry cycles, as these clays form preferentially during alternating periods of saturation and desiccation. The rover's ChemCam instrument detects elevated concentrations of sulfur and chlorine in certain channel deposits, signatures of evaporative concentration as water volumes decreased. These chemical gradients tell the story of a dying river system, where diminishing flows became increasingly saline as dissolved minerals concentrated in shrinking pools. The final stages of channel activity appear to have involved hypersaline brines that deposited unusual sulfate minerals as they evaporated to dryness. There remains uncertainty about the climate mechanisms that sustained liquid water on early Mars. Global climate models struggle to maintain surface temperatures above freezing under the faint young sun that illuminated the early solar system. Yet the geological evidence for flowing water appears unambiguous, creating one of planetary science's most persistent puzzles. Perhaps greenhouse gases provided additional warming, or maybe the water flows occurred during brief periods of volcanic heating that temporarily thawed frozen ground. The preservation of organic carbon in similar geological settings on Earth raises intriguing possibilities for these Martian deposits. River systems concentrate organic matter through transport and burial processes, creating environments where biosignatures might survive for billions of years. The chemical conditions recorded in these channel deposits suggest pH levels and salinity ranges that could have supported microbial life, though detecting such ancient biosignatures remains beyond current instrumental capabilities. Perseverance documents each channel feature with methodical precision, building a comprehensive archive of Martian fluvial morphology. The rover's navigation cameras capture stereoscopic images that allow Earth-based researchers to construct detailed three-dimensional models of channel cross-sections and flow patterns. These digital reconstructions will enable future studies of Martian hydraulics using computational fluid dynamics models that can simulate ancient flow conditions. Only took 4 billion years for running water to become the most alien feature on Mars. The silence that now fills these channels carries no echo of the sounds that once reverberated through them: the splash of water over stone, the rumble of sediment transport during flood stages, the gentle murmur of base flow during dry seasons. The acoustic environment of flowing rivers has vanished from Mars so completely that even the memory of those sounds exists only in stone. The canyon walls rise on either side of Perseverance like the ribs of some vast fossil organism, their exposed layers chronicling the planet's transition from a world where water carved stone to one where only wind shapes the surface. Each stratum represents a chapter in Mars' environmental history, written in the language of minerals and preserved in the patient archive of sedimentary rock. The rover moves through this geological library like a reader turning pages, deciphering the story of water's gradual retreat from a planet that once knew the luxury of abundant surface liquids. The blue-green formations embedded in the canyon wall reveal their secrets slowly, one laser pulse at a time. Perseverance's SuperCam instrument fires focused beams of coherent light at the crystalline deposits, each pulse vaporizing microscopic amounts of material that emit characteristic wavelengths as they cool. The resulting plasma spectra appear on monitors at the Jet Propulsion Laboratory as peaks and valleys that correspond to specific elements: copper, sulfur, magnesium, and water molecules bound within crystal lattices that formed when Mars still possessed a substantial atmosphere. These hydrated sulfate minerals represent some of the most complex chemical formations yet discovered on Mars. Unlike the simple ion oxides that give the planet its characteristic red coloration, these compounds required specific conditions of temperature, pressure, and chemical activity to form. The copper content suggests interaction with hydrothermal systems, underground networks of heated groundwater that carried dissolved metals through porous rock before depositing them in surface expressions. Each crystal preserves a record of the water chemistry that created it, like a molecular diary written in stone. The spectroscopic signatures match closely with minerals found in Earth's Atacama Desert, where copper sulfate deposits form through groundwater evaporation in one of the planet's most arid regions. Yet, the Martian formations show subtle differences in their hydration states and crystal structures, variations that speak to formation under atmospheric conditions that no longer exist anywhere in the solar system. The lower atmospheric pressure on ancient Mars would have affected the stability of different hydration phases, creating mineral assemblages that serve as proxies for paleo-environmental conditions. Pixel's X-ray imaging reveals the internal architecture of these formations with unprecedented detail. Individual crystals show concentric growth patterns reminiscent of tree rings, each layer recording changing chemical conditions as groundwater composition evolved over time. Some crystals display evidence of dissolution and reprecipitation, suggesting cyclical wet-dry periods that allowed mineral structures to develop, partially dissolve, then reform under slightly different conditions. This cyclical pattern implies seasonal or longer-term climate variations that affected groundwater chemistry. The precision required to analyze these microscopic features represents a technological achievement that would have seemed impossible during the early decades of space exploration. PXL can map elemental distributions at the scale of individual crystal faces, revealing chemical gradients and compositional zonation that provide insights into formation mechanisms. Only took 50 years of planetary exploration to develop instruments sensitive enough to perform laboratory quality analysis on rocks separated by interplanetary distances. Mission geologists compare the mineral assemblages to similar formations in terrestrial environments, seeking analogues that might illuminate the conditions under which the Martian deposits formed. The closest Earth parallels occur in geothermal areas where underground hot springs deposit sulfate minerals as they reach the surface and cool. These environments support diverse microbial communities that use the chemical energy of dissolved minerals to power their metabolism, raising intriguing questions about the biological potential of ancient Martian groundwater systems. The water content preserved within these crystal structures provides direct evidence for the availability of liquid water during their formation. Hydrated minerals act as time capsules, trapping water molecules within their atomic frameworks, where they remain stable for billions of years. Spectroscopic analysis can determine not only the presence of water, but also its isotopic composition, which carries information about the source of the water and the environmental conditions under which it was incorporated into the crystal lattice. There remains uncertainty about the duration of water activity required to form such complex mineral assemblages. Laboratory experiments suggest that similar formations require hundreds to thousands of years of sustained water-rock interaction, implying that Mars maintained stable hydrological conditions for extended periods during its early history. This contradicts some atmospheric models that suggest only brief episodes of surface water activity, creating an ongoing debate about the nature and longevity of Mars's ancient climate. The irony of these discoveries lies in their preservation through planetary death. The same processes that ended Mars's active hydrological cycle also created the conditions necessary to preserve these mineral formations for billions of years. The loss of atmospheric water vapor eliminated the chemical weathering processes that would have gradually destroyed these delicate structures, while the cessation of tectonic activity prevented their burial or metamorphic alteration. Only took the complete desiccation of a planet to create perfect preservation conditions for its hydrological history. Perseverance's drill system prepares to extract samples from these formations, a process that requires extraordinary precision to avoid contamination while preserving the delicate crystal structures. The drill bits rotate at carefully controlled speeds to minimize heating that might alter the mineral phases, while pressurized gas flows remove cuttings without introducing terrestrial contamination. Each sample represents a potential time machine, carrying molecular-scale information about Mars's environmental conditions billions of years into the future. The sampling process itself becomes a meditation on the scales of time and space that govern planetary evolution. The rover operates with mechanical patience, each movement calculated to maximize scientific return while preserving irreplaceable geological specimens. The drill extends slowly into formations that took millennia to develop, extracting material that will be studied for decades using analytical techniques that have not yet been invented. Trace element analysis reveals the presence of rare earth elements and heavy metals that could only have been concentrated through hydrothermal processes. These chemical signatures suggest that the groundwater systems responsible for these formations were connected to deep crustal sources, perhaps associated with the volcanic activity that characterized early Mars. The metal concentrations provide constraints on the temperature and pH of the ancient groundwater, parameters that help define the habitability potential of these environments. Only took 1 billion years for chemistry to become archaeology on Mars. The blue-green crystals maintain their molecular structures with crystalline patience, indifferent to the passage of geological epochs that transformed their planet from a world of flowing water to a monument of mineral preservation. They represent both memory and prophecy memory of conditions that once existed, and prophecy of discoveries yet to come, as human understanding of planetary geochemistry continues to evolve through the patient examination of stones that traveled across space and time to reveal their secrets. The chemistry of evaporation operates according to principles that transcend planetary boundaries, yet each world adds its own signature to the process. As ancient Martian groundwater emerged at the surface through springs and seeps, it carried a dissolved cargo of metals and salts accumulated during its journey through subsurface rock formations. The lower atmospheric pressure on early Mars meant that water boiled at temperatures far below Earth's standard, creating unique conditions for mineral precipitation that left chemical fingerprints unlike anything found in terrestrial environments. Perseverance's instruments detect the layered architecture of these evaporate sequences, each stratum representing a different stage in the concentration process. The bottommost layers contain minerals that precipitate first from dilute solutions, primarily gypsum and other simple sulfates that require minimal evaporation to reach saturation. Higher in the sequence, more exotic compounds appear polyhydrated sulfates that form only under specific temperature and humidity conditions. Their crystal structures, preserving information about the atmospheric water vapor content during their formation. The copper-bearing minerals that give these formations their distinctive blue-green coloration represent the final stages of the evaporation process. Copper sulfates possess high solubility compared to other metal compounds, remaining dissolved in groundwater long after iron, calcium, and magnesium have precipitated out as separate mineral phases. Only when evaporation concentrated the remaining brines to extraordinary levels did the copper finally crystallize, creating the sapphire-hued deposits that now catch the pale Martian sunlight like fragments of a vanished ocean. Spectroscopic analysis reveals the presence of hydrated phases that contain multiple water molecules within their crystal structures. These minerals formed under conditions where atmospheric humidity provided a constant source of water vapor to balance the ongoing evaporation process. The delicate equilibrium between water loss and water gain created an environment where complex hydrated compounds could achieve stability, their formation requiring precise atmospheric conditions that existed briefly in Mars's geological history. The mathematical relationships governing evaporative mineral sequences remain constant across planetary environments, yet the specific compounds that form depend entirely on the chemistry of the parent water and the physical conditions during precipitation. On Earth, similar evaporation sequences in closed basins produce predictable mineral assemblages that geochemists can use to reconstruct ancient lake chemistry. The Martian sequences follow the same thermodynamic principles, but yield mineral combinations that reflect the unique composition of Martian groundwater and the planet's distinctive atmospheric evolution. Mission scientists calculate the water volumes required to produce the observed mineral deposits, arriving at estimates that suggest substantial groundwater reservoirs beneath the ancient Martian surface. The mass balance equations indicate that each square meter of mineral deposits represents the evaporation of water columns several meters deep, implying either very long-duration seepage from modest springs or shorter-duration discharge from more vigorous groundwater systems. Only took a planetary water cycle to create chemistry sets that would puzzle geologists billions of years later. The preservation of delicate hydrated phases presents a paradox that challenges current understanding of Mars's atmospheric evolution. These water-bearing minerals should have gradually dehydrated as Mars lost its atmosphere and surface pressures dropped below the stability fields for hydrated compounds. Yet, many crystals retain their water content, suggesting either more recent formation than previously thought or exceptional preservation conditions that prevented dehydration over geological timescales. Laboratory experiments attempting to replicate Martian evaporation conditions face fundamental challenges related to the planet's unique atmospheric composition and pressure regime. Terrestrial vacuum chambers can simulate the low-pressure environment, but reproducing the precise gas composition and trace constituent concentrations of ancient Mars requires sophisticated experimental setups. These studies suggest that the Martian evaporation process occurred under conditions that have no exact analog in Earth's current environment. The irony of studying these ancient chemical processes lies in their revelation through instruments that themselves depend on precise chemical analysis. SuperCam's laser-induced breakdown spectroscopy operates by creating miniature plasma events that reach temperatures of tens of thousands of degrees, temporarily recreating stellar conditions to analyze minerals that formed through gentle evaporation under a dim young sun. Only took 4 billion years of planetary evolution to develop technology capable of reading the chemical signatures of its own deep past. Trace element distributions within individual crystal faces reveal episodic changes in groundwater chemistry that suggest multiple sources contributing to the surface discharge. Some layers show elevated concentrations of elements typical of volcanic groundwater, while others display signatures consistent with deeper crustal sources. This chemical variability implies a complex subsurface hydrology where different groundwater flow paths converged at surface discharge points, creating opportunities for diverse geochemical processes. The stable isotope signatures preserved within these formations provide additional constraints on the temperature and source of the ancient groundwater. Oxygen isotope ratios reflect the temperature of mineral formation, while sulfur isotopes carry information about the source rocks through which the groundwater flowed. These isotopic fingerprints suggest formation temperatures consistent with modest geothermal heating rather than the extreme temperatures associated with active volcanism. Perseverance's analytical suite documents the spatial distribution of different mineral phases within the evaporate sequence, revealing patterns that reflect the hydrodynamics of the ancient discharge environment. Minerals that crystallize rapidly from supersaturated solutions occur in different locations than those that form through slow precipitation from near equilibrium conditions. This spatial organization provides insights into flow velocities, residence times, and mixing processes that characterize the groundwater discharge. There remains uncertainty about the timescales over which these evaporation sequences developed. Some mineral textures suggest rapid precipitation during brief discharge events, while others show evidence of slow crystallization over extended periods. The coexistence of these different formation styles within the same outcrop implies complex temporal variations in groundwater discharge, possibly related to climate cycles or seasonal variations in subsurface hydrology. Only took the death of an atmosphere to preserve perfect examples of planetary geochemistry in action. The blue-green crystals maintain their chemical compositions with molecular precision, each atom locked in place by crystalline forces that have remained stable across eons of planetary change. They represent libraries of information about processes that operated when Mars was young. Their chemical messages waiting patiently for readers equipped with the instruments and knowledge necessary to decode the stories written in their atomic arrangements. Across the vast expanses of Earth's most arid regions, similar mineral formations tell stories of water's patient retreat from landscapes that once knew abundance. In the Atacama Desert of Chile, copper sulfate deposits gleam with the same blue-green luminescence that Perseverance now documents on Mars. Their crystalline structures formed through processes that mirror those occurring on the red planet billions of years ago. These terrestrial analogues provide a reference framework for understanding the Martian discoveries. Yet each world's unique conditions create subtle variations that reveal the distinctive character of planetary evolution. The Atacama's evaporate sequences formed over timescales that span thousands of years, as groundwater moved through copper-rich ore deposits before reaching the surface through springs and seeps. The extreme aridity of this region preserves delicate mineral formations that would dissolve rapidly in more humid environments, creating natural laboratories where researchers can study evaporation processes under conditions approaching those of ancient Mars. The mineral assemblages include many of the same compounds detected by Perseverance, though in different proportions that reflect Earth's higher atmospheric pressure and distinct groundwater chemistry. Spectroscopic analysis of Atacama deposits reveals formation temperatures slightly higher than those indicated by the Martian minerals, a difference attributable to Earth's more substantial atmosphere and closer proximity to the Sun. The terrestrial formations also show evidence of seasonal variations in mineral precipitation, with different compounds crystallizing during wet and dry periods of the region's minimal precipitation cycle. These seasonal signatures provide insights into the potential for similar cyclical processes on ancient Mars, where orbital variations might have created periodic changes in surface conditions. The preservation potential of hydrated minerals varies significantly between Earth and Mars, with the red planet's thin atmosphere providing superior long-term stability for water-bearing compounds. Terrestrial evaporates experience constant chemical weathering due to atmospheric humidity and occasional precipitation events that dissolve and reprecipitate mineral phases. The Martian formations exist in a chemical stasis that has persisted for billions of years. Their molecular structures frozen in configurations that reflect the atmospheric conditions of their formation. Death Valley's salt flats offer another terrestrial analog for Martian evaporation processes. Though the mineral assemblages differ due to distinct source rock chemistry and hydrological settings, the playa lakes of this region concentrate dissolved salts through evaporation, creating zonation patterns where different minerals precipitate at different distances from water sources. These spatial distributions mirror the layered sequences observed in Martian evaporates, suggesting similar physical processes operating under different planetary conditions. Mission geologists construct detailed comparisons between terrestrial and Martian evaporate textures, seeking patterns that might reveal formation mechanisms not apparent from studying either environment in isolation. The crystal habits of Martian sulfates show distinctive features that reflect formation under low atmospheric pressure, with crystal faces and growth patterns that differ subtly from their terrestrial counterparts. Only took a billion years of separate planetary evolution to create mineral museums that preserve the distinctive signatures of each world's environmental history. The kinetics of mineral precipitation operate according to universal chemical principles, yet the specific pathways followed depend critically on environmental conditions such as temperature, pressure, and solution composition. Laboratory experiments designed to simulate Martian evaporation conditions reveal precipitation sequences that match the observed mineral assemblages, providing confidence in interpretations of the ancient environmental conditions. These controlled studies also identify intermediate phases that might have formed temporarily before dissolving or transforming into more stable compounds. Trace element chemistry provides additional insights into the similarities and differences between terrestrial and Martian evaporation processes. The Martian formations contain distinctive ratios of rare Earth elements that reflect the composition of ancient Martian crust, while terrestrial analogues show patterns typical of Earth's continental geology. These chemical fingerprints serve as planetary identification markers, allowing researchers to distinguish between indigenous Martian processes and potential terrestrial contamination in future return samples. The irony of using Earth's driest places to understand Mars's wettest period reflects the temporal scales over which planetary environments evolve. Earth's deserts represent temporary features that will disappear as continental drift and climate change reshape the planet's surface, while Mars's evaporate deposits preserve permanent records of hydrological processes that ended billions of years ago. Only took the complete desiccation of one planet to create the perfect preservation conditions for understanding water's role in planetary evolution. Microbiological studies of terrestrial evaporate environments reveal diverse communities of extremophile organisms that thrive in the high salinity conditions associated with mineral precipitation. These findings raise intriguing questions about the biological potential of ancient Martian groundwater systems, where similar chemical conditions might have supported microbial life during the planet's early history. The preservation of organic compounds in terrestrial evaporates suggests that Martian formations might retain biosignatures if life ever existed in these environments. Perseverance's documentation of the Martian evaporate sequences provides unprecedented detail about mineral textures and associations that would be impossible to study through telescopic observations or orbital remote sensing. The rover's ability to examine individual crystal faces and measure elemental distributions at microscopic scales reveals formation details that rival those obtainable through direct laboratory analysis of terrestrial samples. This level of analytical precision transforms Mars exploration from reconnaissance to detailed field geology. Seasonal variations in terrestrial evaporate formation suggest potential mechanisms for the cyclical mineral deposition observed in Martian sequences. Earth's desert regions experience subtle changes in groundwater chemistry related to seasonal temperature variations and occasional precipitation events. Similar processes on ancient Mars might have been driven by orbital cycles that periodically change the planet's climate, creating the layered mineral sequences now preserved in canyon walls. There remains uncertainty about the biological implications of the chemical similarities between terrestrial and Martian evaporate environments. While Earth's high salinity mineral deposits support specialized microbial communities, the environmental conditions on ancient Mars might have exceeded the tolerance limits of any potential life forms. The chemical signatures preserved in Martian evaporates provide constraints on ancient water activity and salinity levels that help define the habitability potential of these environments. Only took 4 billion years for two planets to create complementary libraries of evaporation chemistry. Earth's active processes continue to form new evaporate deposits while gradually destroying older ones, maintaining a dynamic record of current environmental conditions. Mars preserves its ancient formations with crystalline patience, offering permanent access to chemical information about processes that operated when the solar system was young and both planets possessed abundant surface water under skies that no longer exist. The distinctive sapphire coloration that gives these Martian formations their otherworldly beauty emerges from copper atoms embedded within sulfate crystal lattices, their electronic structures absorbing red wavelengths while reflecting the blue-green portions of the electromagnetic spectrum. This copper signature tells a story that extends far beyond mere aesthetic appeal, revealing the presence of hydrothermal processes that once operated beneath Mars' ancient surface. The metal concentrations required to produce such vivid coloration indicate groundwater systems that achieved temperatures and chemical conditions capable of leaching copper from deep crustal sources. Perseverance's detailed spectroscopic analysis reveals multiple copper-bearing phases within the evaporate sequence, each representing different stages in the hydrothermal evolution of the ancient groundwater system. The earliest formed minerals contain copper in oxidation, states that suggest reducing conditions during initial precipitation, while later phases show progressive oxidation as the groundwater chemistry evolved in response to changing atmospheric conditions. This chemical progression provides insights into the redox evolution of Mars' early environment. Hydrothermal systems require specific geological conditions to develop and maintain the elevated temperatures necessary for extensive metal leaching. On Earth, such systems typically occur near volcanic centers or in regions of elevated geothermal gradient where deep groundwater circulation can access heat sources within the crust. The presence of copper-rich evaporates on Mars suggests similar conditions existed during the planet's early history, implying active geological processes that created and sustained subsurface thermal anomalies. The copper concentrations detected by PXL exceed those typically found in terrestrial evaporate deposits, suggesting either exceptionally copper-rich source rocks or hydrothermal processes that achieved unusual efficiency in metal extraction and transport. Mission geologists calculate that the observed copper content requires groundwater temperatures of at least 60 to 80 degrees Celsius, substantially above the freezing point even under the reduced atmospheric pressure conditions of early Mars. Only took 1 billion years for planetary cooling to transform active geothermal systems into mineral museums, preserving evidence of their former existence. Laboratory studies of copper sulfate formation under simulated Martian conditions reveal crystallization pathways that differ from those operating under terrestrial atmospheric pressures. The lower pressure environment affects both the solubility of copper compounds and the stability of different hydration phases, creating opportunities for mineral assemblages that cannot form under Earth's current atmospheric conditions. These experimental results support interpretations of the Martian deposits as products of unique environmental conditions. The spatial distribution of copper-rich phases within the evaporate sequence reflects the thermal structure of the ancient hydrothermal system. Higher copper concentrations occur in mineral layers that formed during periods of elevated groundwater temperature, while lower concentrations characterize phases that precipitated as the system cooled. This thermal evolution suggests either episodic volcanic heating or gradual cooling as Mars' internal heat production declined over geological time. Trace element analysis reveals the presence of other metals typically associated with hydrothermal systems, including zinc, lead, and traces of precious metals that require high-temperature water-rock interaction to mobilize. These additional metal signatures strengthen interpretations of hydrothermal origin while providing constraints on the temperature and chemistry of the ancient groundwater. The metal ratios match those found in terrestrial geothermal systems, suggesting similar processes operating under different planetary conditions. The irony of discovering evidence for past hydrothermal activity on a planet, now characterized by extreme cold and aridity, highlights the dramatic environmental changes that can occur over planetary timescales. Mars once possessed subsurface thermal systems capable of maintaining liquid water at temperatures suitable for extensive geochemical processes. Yet these same systems ultimately contributed to atmospheric loss through enhanced volcanic outgassing that was subsequently lost to space. Crystallographic analysis of the copper-bearing phases reveals structural details that provide insights into formation temperatures and pressure conditions. The specific crystal modifications present in the Martian deposits correspond to stability fields that existed under the atmospheric conditions of early Mars, offering independent confirmation of paleo-environmental reconstructions based on other geological evidence. These mineralogical constraints help define the physical conditions under which ancient Martian hydrothermal systems operated. There remains uncertainty about the energy sources that powered these ancient hydrothermal systems on Mars. While volcanism provides an obvious mechanism for subsurface heating, the timing and distribution of volcanic activity during Mars's early history remain subjects of ongoing research. Alternative energy sources might include radioactive decay in crustal rocks or impact heating from the heavy bombardment period that characterized the early solar system. The preservation of delicate copper sulfate crystals over billions of years requires exceptional chemical stability that reflects the unique preservation environment of modern Mars. The absence of liquid water eliminates dissolution processes that would gradually destroy these formations on Earth, while the thin atmosphere minimizes chemical weathering that might alter their compositions. Only took the death of a planet's hydrological cycle to create perfect preservation conditions for its hydrothermal heritage. Perseverance's high-resolution imaging reveals microscopic textures within the copper-bearing crystals that provide additional information about formation conditions. Some crystals show evidence of rapid growth from supersaturated solutions, while others display slow crystallization textures indicative of equilibrium precipitation. These textural variations suggest fluctuating discharge conditions in the ancient hydrothermal system, possibly related to changes in subsurface pressure or temperature. The habitability implications of hydrothermal environments have captured the attention of astrobiologists studying the potential for ancient life on Mars. Terrestrial hydrothermal systems support diverse microbial communities that derive energy from chemical reactions involving dissolved metals and sulfur compounds. The chemical conditions preserved in these Martian evaporites suggest similar energy sources might have been available to support metabolism if life ever existed in these environments. Modern analog studies in terrestrial geothermal areas reveal that copper-rich hydrothermal systems can support specialized microbial communities adapted to high metal concentrations and elevated temperatures. These extremophile organisms use copper as an electron acceptor in their metabolic processes, creating the possibility that similar biochemical pathways might have operated in ancient Martian hydrothermal systems. The preservation potential for biosignatures in copper-rich evaporite deposits remains an active area of research. Only took the discovery of blue stones on a red planet to reveal the hidden thermal history of another world. The copper-bearing crystals maintain their metallic memories with atomic precision, each metal atom positioned according to crystal chemical rules that operated when Mars possessed the geological vigor to maintain subsurface thermal systems. They represent both endings and beginnings, the end of Mars's active hydrothermal period, and the beginning of human understanding of planetary thermal evolution through the patient examination of minerals that preserve their formation stories in crystalline detail. The drill bit penetrates Martian stone with mechanical deliberation, each rotation carving through mineral layers that chronicle the planet's transition from a world of flowing water to its current state of crystalline preservation. Perseverance's percussion drill operates at precisely controlled speeds to minimize heating that might alter the delicate chemical phases within the evaporate sequence, while jets of pressurized nitrogen gas carry away drill cuttings without introducing terrestrial contamination. The drilling process itself becomes a journey through time, with each millimeter of penetration revealing older layers of the ancient evaporation sequence. The drill core emerges in segments that preserve the original layered structure of the evaporite deposit, each stratum representing a different episode in the chemical evolution of the ancient groundwater system. High-resolution imaging of the core surface reveals microscopic details invisible from orbital perspectives or even surface photography. Individual crystal faces catch the filtered Martian sunlight. their orientations and size distributions providing insights into the nucleation and growth processes that operated during mineral precipitation. PXL's elemental mapping of the drill core cross-section reveals chemical gradients that document changing groundwater composition over time. The deepest layers contain simple sulfate minerals that precipitated from relatively dilute solutions, while progressively higher layers show increasing complexity in their mineral assemblages as evaporative concentration proceeded. The chemical evolution recorded in these layers provides a detailed history of groundwater chemistry that spans potentially thousands of years of active discharge. Laboratory protocols developed for analyzing similar terrestrial samples guide the interpretation of these Martian drill cores, though the unique environmental conditions of Mars require careful consideration of formation processes that have no exact terrestrial analogues. The preservation of original depositional textures in the Martian samples exceeds that typically found in Earth's geological record, where ongoing weathering and diagenetic processes gradually modify primary mineral assemblages. Only took the complete cessation of surface water activity to create optimal preservation conditions for studying evaporate formation processes. Microscopic examination of individual drill particles reveals internal structures that preserve information about the crystallization environment during mineral formation. Some grains show evidence of rapid precipitation from supersaturated solutions, their crystal faces displaying growth steps and surface irregularities characteristic of disequilibrium conditions. Other particles exhibit the smooth faces and regular geometries typical of slow crystallization from near equilibrium solutions. Suggesting temporal variations in the chemical state of the ancient groundwater, the drilling operation generates data that extends far beyond the immediate core samples, with sensors monitoring drilling resistance, temperature changes, and gas emissions that provide additional information about subsurface conditions. Variations in drilling hardness correlate with changes in mineral composition and porosity, revealing the physical properties of different evaporate layers. These engineering measurements complement the chemical and mineralogical data to provide a comprehensive characterization of the subsurface environment. Spectroscopic analysis of fresh drill surfaces eliminates the potential interference from surface weathering products and dust coatings that might obscure the original mineral compositions. The newly exposed surfaces reveal pristine mineral phases that have remained unaltered since their formation billions of years ago, providing direct access to ancient environmental conditions without the complications introduced by subsequent modification processes. This analytical advantage represents one of the key benefits of drilling compared to surface-only investigations. The irony of destroying ancient geological formations to understand their formation processes reflects the fundamental challenge of planetary science, where sampling requires the permanent alteration of irreplaceable natural archives. Each drill core represents both scientific opportunity and irreversible change, as the act of extraction inevitably modifies the geological context that preserved these formations for billions of years. Only took human curiosity to transform permanent planetary records into temporary scientific specimens. Volatile analysis of the drill samples reveals the presence of water and other gases trapped within crystal structures and fluid inclusions formed during the original precipitation process. These molecular remnants provide direct samples of the ancient Martian atmosphere and groundwater, though in quantities measured in parts per million rather than the substantial volumes that once flowed across the planet's surface. The isotopic compositions of these trapped volatiles carry information about the source and evolution of Mars's early atmosphere. Statistical analysis of crystal size distributions within the drill cores provides insights into the nucleation and growth kinetics that controlled mineral precipitation in the ancient evaporate environment. Mathematical models developed for terrestrial evaporate systems predict specific relationships between crystal size and formation time, allowing researchers to estimate the duration of active precipitation periods. These temporal constraints help define the longevity of water activity required to produce the observed mineral assemblages. There remains uncertainty about the spatial extent of the hydrothermal system that fed these evaporate deposits. The drill cores provide detailed information about conditions at a single location, but extrapolating these findings to regional or global scales requires additional data from multiple sites. Future missions may target similar formations in other locations to determine whether these deposits represent local phenomena or evidence for planet-wide hydrothermal activity. The sample collection system aboard Perseverance operates with extraordinary precision to preserve the chemical and physical integrity of the drill cores during storage and eventual return to Earth. Each sample tube undergoes hermetic sealing under ultra-clean conditions to prevent contamination while maintaining the original atmospheric environment of the drilling site. These preserved samples will eventually undergo analysis using laboratory techniques that exceed the capabilities of any rover-mounted instrument. Comparative analysis of different layers within the same drill core reveals episodic changes in evaporation rate and groundwater chemistry that suggest variable discharge conditions over time. Some layers show evidence of rapid mineral precipitation during periods of vigorous groundwater flow, while others indicate slow crystallization during intervals of reduced discharge. This temporal variability implies complex controls on the ancient hydrothermal system, possibly related to climate variations or changes in subsurface permeability. Trace organic analysis of the drill samples represents one of the most sensitive measurements attempted by any Mars mission, with detection limits approaching those achievable in terrestrial laboratories. While no definitive organic signatures have been detected, the analytical techniques continue to improve with each sample analysis. The chemical environment preserved in these evaporate deposits represents one of the most promising targets for organic preservation on Mars. Only took 50 years of technological development to create drilling systems capable of operating across interplanetary distances under robotic control. The drill cores extracted from these ancient Martian formations represent some of the most precisely collected geological samples in the history of planetary exploration, their preservation and analysis requiring coordination between robotic systems on Mars and laboratory facilities on Earth, separated by hundreds of millions of kilometers and decades of transit time. The microscopic landscape revealed within these ancient Martian formations unfolds like a hidden universe of crystalline architecture, each structure preserving information about water chemistry and atmospheric conditions that existed when the solar system was less than half its current age. Perseverance's Mahlai instrument captures images at resolutions that approach the theoretical limits of optical microscopy, revealing crystal faces, growth patterns, and textural relationships that would challenge the capabilities of many terrestrial laboratories. Individual mineral grains display internal zonation patterns that chronicle changing chemical conditions during their formation, creating microscopic libraries of environmental information. The internal architecture of copper sulfate crystals shows remarkable preservation of primary growth features that typically disappear during post-depositional alteration processes. Concentric growth bands within individual crystals record fluctuations in copper concentration and crystallization rate, suggesting episodic changes in the hydrothermal system that fed these surface deposits. Some crystals display hopper structures and skeletal growth patterns characteristic of rapid precipitation from highly supersaturated solutions, while others show the euhedral faces and uniform extinction patterns typical of slow equilibrium crystallization. High magnification imaging reveals the presence of microscopic fluid inclusions trapped within crystal lattices during mineral formation. These tiny cavities contain samples of the original groundwater from which the crystals precipitated, preserved for billions of years within their crystalline hosts. While the inclusions are too small for direct chemical analysis using current rover instrumentation, their size distributions and spatial arrangements provide insights into the temperature and pressure conditions during crystal growth. The textural relationships between different mineral phases preserve information about the sequence of precipitation events that occurred during evaporative concentration of the ancient groundwater. Early formed gypsum crystals show evidence of partial dissolution and replacement by later copper sulfate phases, indicating changing solution chemistry as evaporation proceeded. These replacement textures document the chemical evolution of the brine as it concentrated through progressive water loss. Crystallographic orientation analysis reveals preferred alignments of mineral grains that reflect the flow directions and hydraulic gradients present during deposition. The statistical analysis of crystal orientations provides insights into the hydrodynamics of the ancient discharge environment, including flow velocities and turbulence patterns that influenced mineral nucleation and growth. Only took 4 billion years for flowing water to become fossilized geometry, its former motion preserved in the atomic arrangements of minerals that crystallized from its dissolved cargo. Surface morphology studies of individual crystal faces reveal growth steps, spiral dislocations, and other features that provide insights into the molecular scale processes that controlled crystallization. These microscopic surface features preserve information about crystal growth mechanisms that operated under the unique environmental conditions of ancient Mars. The preservation of such delicate surface structures indicates minimal post-depositional alteration, confirming the exceptional chemical stability of these formations. Electron microscopy analogs from terrestrial laboratories provide reference frameworks for interpreting the textural features observed in the Martian samples, though direct comparison requires careful consideration of the different formation environments. The Martian textures show distinctive characteristics that reflect crystallization under low atmospheric pressure and unique solution chemistry, creating mineral fabrics that have no exact terrestrial counterparts. These textural differences serve as fingerprints of the specific environmental conditions that existed on early Mars. The irony of studying ancient water through the examination of completely desiccated minerals reflects the temporal scales over which planetary environments evolve. The crystal structures that now preserve information about Mars's hydrological past formed through processes that simultaneously contributed to the planet's water loss. As surface evaporation gradually transferred atmospheric moisture to space, only took the death of planetary hydrology to create perfect preservation conditions for studying its former existence. Scanning electron microscopy techniques adapted for use in the low-pressure environment of Mars require sophisticated instrumental designs that can operate reliably under conditions that would disable conventional terrestrial equipment. The engineering challenges of maintaining high-vacuum electron optics while operating in Mars's thin atmosphere represent significant technological achievements that extend the capabilities of planetary exploration beyond what seemed possible during earlier mission eras. Statistical analysis of crystal size distributions reveals bimodal populations that suggest multiple nucleation events during the formation of these deposits. Some size fractions show characteristics typical of heterogeneous nucleation on pre-existing surfaces, while others indicate homogeneous nucleation in supersaturated solutions. These nucleation mechanisms provide insights into the degree of supersaturation and the availability of nucleation sites during mineral precipitation. There remains uncertainty about the role of organic compounds in influencing crystal morphology and growth rates in these ancient Martian systems. Terrestrial studies demonstrate that dissolved organic matter can significantly affect mineral precipitation processes, creating distinctive textural features that persist through geological time. The search for similar organic influences in Martian evaporite textures represents an ongoing challenge for astrobiology research. Microgeochemical analysis using laser ablation techniques reveals elemental variations within individual crystals that document changing solution composition during growth. These intracrystalline chemical gradients preserve information about mixing processes, temperature fluctuations, and evolving redox conditions in the ancient groundwater system. The chemical zonation patterns serve as microscopic recorders of environmental change that operated on timescales ranging from hours to centuries. Porosity analysis of the evaporate sequences reveals interconnected networks of microscopic voids that may have facilitated fluid migration and chemical exchange during and after mineral formation. These pore systems could have provided pathways for late-stage fluid circulation that modified the original chemical compositions, though the extent of such alteration appears minimal based on the preservation of primary depositional textures. Comparative studies of crystal morphology between different layers within the evaporate sequence reveal systematic changes in crystallization conditions over time. Early layers show evidence of formation under relatively dilute conditions with abundant nucleation sites, while later layers display textures characteristic of precipitation from increasingly concentrated brines with limited nucleation opportunities. This temporal evolution reflects the progressive concentration of the groundwater system as discharge volumes declined. Microfossil search protocols developed for terrestrial evaporate deposits guide the examination of these Martian samples for potential biosignatures, though the detection limits and preservation potential under Martian conditions remain subjects of ongoing research. The microscopic scale of potential biological structures requires analytical techniques that approach the fundamental limits of optical and chemical detection, challenging current instrumentation capabilities. Only took the development of interplanetary microscopy to reveal that mineral formation processes operate according to universal physical principles regardless of planetary setting. The crystalline landscapes preserved within these ancient Martian formations display the same fundamental relationships between nucleation, growth, and environmental conditions that govern mineral formation throughout the cosmos. Their microscopic architectures serving as windows into the chemical processes that shaped planetary surfaces when the solar system was young. The silence that now envelops these Martian canyons carries no memory of the atmospheric tumult that once characterized the planet's weather systems during the Noachian period, when thick clouds gathered above highland regions and seasonal storms redistributed water across continental-scale drainage basins. The evaporate deposits preserve chemical evidence of this vanished meteorology, their mineral assemblages documenting periods of intense precipitation followed by extended droughts that concentrated dissolved salts in temporary lakes and playas scattered across the ancient Martian landscape. Climate models reconstructing Noachian atmospheric conditions struggle to reconcile the geological evidence for abundant liquid water with solar luminosity calculations that suggest Mars should have remained frozen under the faint young sun. The evaporate formations provide crucial constraints for these models, their chemistry indicating surface temperatures and humidity levels that require greenhouse warming mechanisms to maintain stability. The mineral assemblages suggest atmospheric carbon dioxide concentrations substantially higher than current levels. Though the exact values remain subjects of ongoing research and debate, seasonal cyclicity preserved within the layered evaporate sequences reflects orbital variations that influenced Mars's climate during its early history. The planet's obliquity and eccentricity cycles created periodic changes in solar heating that affected atmospheric circulation patterns and regional precipitation rates. These astronomical forcing mechanisms left chemical fingerprints in the evaporate layers, with alternating mineral compositions recording wet and dry phases that followed predictable celestial rhythms. The absence of impact craters within the canyon deposits indicates rapid sedimentation rates that buried or erased meteorite impacts during the period of active water deposition. This geological observation suggests sustained hydrological activity over timescales measured in hundreds of thousands to millions of years, far exceeding the brief episodes of water activity proposed by some climate models. Only took 1 billion years for planetary weather to become geological speculation, its former vigor preserved only in the chemical compositions of minerals that crystallized from its final exhalations. Paleomagnetic analysis of the evaporate layers reveals information about Mars's ancient magnetic field strength and orientation during the period of water activity. The magnetic minerals preserved within these deposits carry remnant magnetization that reflects the planetary magnetic field configuration when the crystals formed. These magnetic signatures provide constraints on the timing and duration of Mars' magnetic field collapse, which may have contributed to atmospheric loss and climate change. Atmospheric pressure estimates derived from the stability fields of different hydrated mineral phases suggest surface pressures several times higher than current Martian conditions. The presence of certain copper sulfate hydration states requires minimum atmospheric water vapor pressures that could only have existed under a substantially thicker atmosphere. These mineralogical constraints provide independent confirmation of climate models predicting early Mars atmospheric densities sufficient to maintain liquid water stability. The chemical isotope signatures preserved within evaporate minerals document the evolution of Mars' atmospheric composition through time. Carbon isotope ratios reflect the balance between volcanic outgassing and atmospheric escape processes, while sulfur isotopes carry information about the sources and cycling of sulfur compounds in the ancient atmosphere. These isotopic records provide insights into the mechanisms responsible for Mars's atmospheric evolution and eventual loss. There remains uncertainty about the role of impact events in triggering temporary episodes of enhanced atmospheric density and water activity. Large meteorite impacts could have released substantial quantities of water vapor and carbon dioxide from crustal rocks, creating transient greenhouse conditions that allowed liquid water to flow across the surface. The timing of major impact events during the Noachian period coincides with geological evidence for water activity, suggesting possible causal relationships. The irony of studying ancient weather patterns on a planet that now experiences only minimal atmospheric dynamics highlights the dramatic environmental changes possible over geological timescales. Modern Mars possesses weather systems limited to dust storms and seasonal carbon dioxide condensation, while ancient Mars supported precipitation cycles, river flooding, and lake formation that would have created recognizable meteorological phenomena under alien skies. Evaporation rate calculations based on mineral precipitation sequences provide estimates of ancient Martian wind speeds and humidity levels during the final stages of surface water activity. The crystal size distributions and mineral textures indicate specific evaporation rates that can be related to atmospheric conditions through thermodynamic models. These calculations suggest wind speeds comparable to those in Earth's desert regions, implying atmospheric circulation patterns capable of redistributing water vapor across regional scales. Comparative studies of evaporate formation in terrestrial paleolake systems provide analogs for interpreting the Martian deposits. Though differences in atmospheric composition and planetary parameters require careful scaling of terrestrial relationships, Earth's ancient lake systems show similar cyclical deposition patterns related to climate variations, but the specific mineral assemblages differ due to distinct source rock chemistry and atmospheric conditions. Hydrological modeling of the ancient Martian drainage systems suggests that the evaporate deposits formed in terminal basins where rivers and groundwater discharge converged without outlets to larger water bodies. These closed basin environments concentrated dissolved salts through evaporation, creating the chemical conditions necessary for the diverse mineral assemblages observed in the canyon deposits. The hydrology of these systems required sustained water inputs over geological timescales. Sedimentological analysis of the evaporate sequences reveals evidence for periodic flooding events that temporarily diluted the concentrated brines and reset the chemical evolution toward less saline conditions. These flood deposits suggest that the evaporate basins experienced episodic inputs of fresh water, possibly related to overflow from upstream lakes or seasonal snowmelt from highland regions. The preservation of delicate sedimentary structures within the evaporate layers indicates minimal post-depositional disturbance, suggesting that these deposits have remained essentially unchanged since their formation during the Noachian period. This exceptional preservation allows detailed reconstruction of depositional processes and environmental conditions that would be impossible to achieve in more geologically active settings. Trace gas analysis of fluid inclusions within evaporate crystals provides direct samples of the ancient Martian atmosphere, though in quantities too small for detailed analysis using current rover instrumentation. Future laboratory studies of returned samples may be able to extract and analyze these atmospheric remnants, providing unprecedented insights into the composition and evolution of Mars's early atmosphere. Only took the complete transformation of a planetary climate system to create perfect archaeological preservation of its former existence. The evaporate deposits maintain their chemical and textural integrity with crystalline patience, serving as witnesses to atmospheric processes that operated when Mars possessed the meteorological complexity to support water cycles, weather fronts, and seasonal precipitation patterns under skies that held clouds and knew the sound of falling rain. The elemental fingerprints embedded within these ancient Martian formations read like a periodic table written in stone, each trace element carrying information about the geological processes that operated when water moved freely through the planet's crustal rocks. Perseverance's analytical instruments detect minute concentrations of elements that could only have been mobilized and transported by liquid water, their presence serving as unambiguous evidence for sustained aqueous activity during Mars's early history. The chemical signatures reveal not just the existence of ancient water, but its temperature, acidity, and interaction with different rock types during its journey from deep crustal sources to surface evaporation sites. Rare earth element patterns within the evaporate deposits mirror those found in Martian meteorites that have fallen to Earth, confirming that these formations represent indigenous Martian processes rather than contamination from terrestrial sources. The lanthanide series elements display characteristic fractionation patterns that reflect high-temperature water-rock interaction, suggesting that the ancient groundwater systems achieved temperatures of several hundred degrees Celsius in their deep crustal source regions. These elevated temperatures enabled extensive leaching of elements typically resistant to chemical weathering under moderate conditions. Platinum group element concentrations provide insights into the role of meteorite impacts in delivering water and other volatiles to early Mars. The ratios of iridium, osmium, and platinum in the evaporate deposits suggest mixing between crustal sources and materials delivered by asteroid and comet impacts during the late heavy bombardment period. This extraterrestrial component may have contributed significantly to Mars's early water inventory, though the relative importance of internal versus external water sources remains an active area of research. Boron isotope ratios preserved within the evaporate minerals carry information about the pH conditions of the ancient groundwater systems. Boron fractionation during mineral precipitation is highly sensitive to solution acidity, allowing researchers to reconstruct the chemical environment that existed during crystal formation. The isotopic signatures suggest moderately alkaline conditions that would have been compatible with biological processes, though the salinity levels during the final stages of evaporation may have exceeded the tolerance limits of most known life forms. The distribution of volatile elements such as chlorine, bromine, and iodine within different mineral phases reflects the progressive concentration of the ancient brines as evaporation proceeded. These halogens become increasingly enriched in the final precipitation products, creating chemical gradients that document the evolution from dilute groundwater to hypersaline brines. The halogen ratios provide constraints on the degree of evaporative concentration and the original composition of the source groundwater. Trace metal chemistry reveals evidence for redox stratification within the ancient groundwater system, with different oxidation states of iron, manganese, and other redox-sensitive elements occurring in spatially distinct mineral phases. This chemical zonation suggests that the groundwater system maintained distinct geochemical environments where oxygen availability varied according to depth, flow path, and interaction with organic matter or reducing minerals. Only took 1 billion years for chemical gradients to become fossilized redox archaeology, preserving evidence of subsurface environments that supported diverse geochemical processes. Molybdenum and tungsten concentrations provide insights into the temperature and oxygen fugacity conditions during hydrothermal alteration of the source rocks. These elements require specific chemical conditions for mobilization and transport, their presence indicating high-temperature fluid circulation through crustal rocks under reducing conditions. The molybdenum-tungsten systematics suggest interaction with sulfide-bearing rocks at temperatures exceeding 200 degrees Celsius. Phosphorus chemistry within the evaporate deposits reveals information about nutrient availability in the ancient Martian groundwater systems. Phosphorus represents one of the key limiting nutrients for biological processes, and its concentration and speciation in these formations provide constraints on the bioavailability of this essential element. The phosphorus occurs primarily in phosphate minerals that form through precipitation from phosphorus-bearing solutions, suggesting adequate concentrations to support biological processes if other environmental conditions were suitable. The irony of using trace element geochemistry to study ancient habitability lies in the fact that many of these elements would have been toxic to life at the concentrations required for geological detection. The same metal-rich conditions that created distinctive chemical signatures also may have created environmental stress for any potential biological systems. Only took the death of planetary habitability to create optimal preservation conditions for studying ancient environmental chemistry. Lead isotope systematics within the evaporate minerals provide constraints on the age and source of the materials involved in the hydrothermal system. The lead isotope ratios reflect the uranium-thorium lead evolution of the crustal rocks through which the groundwater circulated, allowing researchers to identify specific geological terrains that contributed to the groundwater chemistry. These isotopic signatures suggest interaction with rocks representing multiple episodes of Martian crustal formation. Selenium and tellurium concentrations indicate the involvement of volcanic processes in the hydrothermal system that fed these evaporate deposits. These elements typically occur in elevated concentrations in volcanic gases and hydrothermal fluids, their presence suggesting that magmatic activity contributed heat and chemical components to the groundwater system. The selenium-tellurium ratios provide insights into the temperature and sulfur fugacity conditions during hydrothermal alteration. There remains uncertainty about the role of atmospheric interactions in modifying the trace element chemistry of surface evaporate deposits. Some elements may have been added to or removed from the evaporating brines through reaction with atmospheric gases, potentially altering the chemical signatures that preserved information about subsurface processes. Distinguishing between crustal and atmospheric sources requires careful analysis of element associations and mineral paragenesis. Chromium speciation within the evaporate minerals provides information about the oxidation state of the ancient groundwater and its interaction with mafic and ultramafic rocks. Hexavalent chromium occurs only under highly oxidizing conditions, while trivalent chromium predominates in reducing environments. The chromium oxidation states preserved in these formations suggest fluctuating redox conditions that may have been influenced by biological processes or variations in atmospheric oxygen content. Vanadium chemistry reveals additional information about the redox evolution of the ancient Martian groundwater system. Vanadium occurs in multiple oxidation states that are sensitive to oxygen availability and organic matter content. The vanadium speciation patterns suggest interaction with organic compounds that may have influenced the metal chemistry of the groundwater, though the source and nature of this organic matter remain subjects of speculation. Zinc and cadmium concentrations provide insights into the temperature and salinity conditions during mineral precipitation. These elements show strong partitioning behavior that depends on crystallization temperature and solution composition. The zinc-cadmium ratios in different mineral phases reflect the thermal and chemical evolution of the evaporating brines, providing independent constraints on formation conditions. Noble gas signatures trapped within fluid inclusions preserve samples of the ancient Martian atmosphere, though in quantities approaching the detection limits of current analytical techniques. Future analysis of returned samples may be able to extract and analyze these atmospheric remnants, providing direct information about the composition and isotopic characteristics of Mars's early atmosphere. The noble gas ratios carry information about atmospheric escape processes and the evolution of planetary volatile inventories. Only took 4 billion years for trace element geochemistry to become planetary archaeology, with metal concentrations measured in parts per million, preserving information about processes that operated on global scales when Mars possessed the geochemical vigor to support extensive water-rock interaction. The elemental signatures maintain their chemical integrity with atomic precision, serving as molecular fossils of hydrothermal systems that redistributed crustal components through aqueous solutions under atmospheric conditions that no longer exist anywhere in the solar system. The patience required to decode these ancient chemical messages stretches across months and years of careful analysis, each analytical sequence demanding weeks of preparation before a single laser pulse can interrogate the atomic arrangements preserved within Martian crystals. Scientists at the Jet Propulsion Laboratory coordinate with researchers across multiple continents. Their collaborative efforts spanning time zones and disciplinary boundaries as they slowly extract meaning from spectral peaks and elemental ratios that document processes billions of years removed from direct observation. The analysis proceeds with deliberate, methodical precision, each measurement building upon previous results in an iterative process that gradually reveals the environmental conditions of ancient Mars. Sample preparation protocols developed for terrestrial meteorite analysis provide frameworks for interpreting the Martian data, though the unique formation conditions require constant refinement of analytical approaches and interpretive models. The rover's instruments operate at the limits of their design specifications, extracting maximum information from every observation while conserving power and data transmission capacity for the most scientifically valuable measurements. Each analytical session represents a carefully choreographed sequence of instrument operations optimized for specific scientific questions. Statistical analysis of the accumulated data reveals patterns that emerge only through the examination of hundreds of individual measurements across multiple mineral phases and geological settings. Machine learning algorithms trained on terrestrial geochemical databases identify subtle correlations between elemental associations that might escape recognition through traditional analytical approaches. These computational tools help researchers recognize geological processes that operated under environmental conditions for which Earth provides no exact analogs. The temporal scales of scientific analysis mirror the geological processes they seek to understand. With years of laboratory work required to decode information about processes that operated over millennia, graduate students begin their doctoral research and analyzing data from formations that crystallized before Earth's oldest rocks formed. Their academic careers devoted to understanding chemical processes that ended billions of years before human civilization began. Only took 50 years of planetary exploration to create scientific questions that will require generations to answer completely. International collaboration networks connect researchers studying these Martian formations with specialists in terrestrial analog systems, creating unprecedented opportunities for comparative planetary geology. The chemical signatures detected by Perseverance receive interpretation through comparison with evaporate deposits from every continent on Earth, each terrestrial analog contributing insights while highlighting the unique aspects of Martian environmental evolution. These collaborative efforts transcend national boundaries in pursuit of understanding planetary processes that operate on cosmic timescales. Instrumental precision requirements for trace element analysis approach the fundamental limits of current analytical technology, with detection limits measured in parts per billion for elements present in vanishingly small concentrations. The signal-to-noise ratios achieved by rover-mounted instruments rival those of dedicated terrestrial laboratories, representing extraordinary engineering achievements that enable quantitative geochemistry across interplanetary distances. Each successful measurement validates decades of technological development and mission planning. The irony of studying ancient environmental conditions through the analysis of completely sterile samples reflects the temporal disconnection between the processes being investigated and the methods used to study them. The formations that once recorded active hydrological cycles now exist in environments more sterile than any terrestrial laboratory, their preservation enabling scientific analysis while eliminating any possibility of ongoing environmental interaction. Database management systems designed to handle the complexity and volume of planetary geochemical data require sophisticated approaches to data storage, retrieval, and analysis that exceed the capabilities of traditional geological databases. The multidimensional nature of the chemical information, combined with spatial and temporal metadata, creates data structures that challenge conventional approaches to scientific data management. These information systems will serve as foundations for future comparative planetology research. Error analysis and uncertainty. Quantification represent critical aspects of interpreting geochemical data collected under the challenging conditions of planetary exploration. Statistical models account for instrumental drift, calibration uncertainties, and environmental factors that affect measurement precision, ensuring that scientific conclusions rest on solid analytical foundations. The propagation of uncertainties through complex interpretive models requires sophisticated mathematical approaches that acknowledge the limitations of remote sensing techniques. There remains uncertainty about the completeness of the geochemical record preserved in these formations, as post-depositional processes may have selectively altered or removed certain chemical signatures while preserving others. Understanding these preservation biases requires detailed knowledge of diagenetic processes that operated under Martian surface conditions, an area of research that remains in its early stages due to limited sample availability and incomplete understanding of Mars's geological evolution. Quality control protocols ensure that the scientific conclusions drawn from these analyses meet the rigorous standards required for planetary science research. Multiple analytical techniques provide independent verification of key results, while blind analysis procedures eliminate potential bias in data interpretation. The scientific process moves with deliberate caution, ensuring that each conclusion can withstand the scrutiny of peer review and independent verification. Archival systems preserve the raw analytical data in formats that will remain accessible to future researchers, equipped with improved analytical techniques and theoretical frameworks. The data represent permanent scientific resources that will support research efforts for decades beyond the operational lifetime of the rover mission. These digital archives ensure that the scientific investment in planetary exploration continues to yield returns long after the original missions conclude. Comparative analysis of chemical signatures from different Martian missions reveals regional variations in ancient environmental conditions that provide insights into the global distribution of habitable environments during Mars' early history. Each landing site contributes unique information about local geological processes while contributing to broader understanding of planetary-scale environmental evolution. The accumulation of data from multiple missions gradually builds comprehensive pictures of ancient Martian environmental conditions. Technological development, inspired by the analytical challenges of planetary exploration, creates innovations that benefit terrestrial geochemical research and other fields requiring ultra-sensitive analytical capabilities. The instrumental techniques developed for Mars exploration find applications in environmental monitoring, materials science, and archaeological research, demonstrating the broader societal benefits of planetary exploration investments. Educational opportunities created by these research efforts train new generations of planetary scientists equipped with interdisciplinary skills spanning geochemistry, astrobiology, and planetary physics. The complexity of interpreting ancient environmental conditions from limited chemical data requires synthetic thinking that draws upon multiple scientific disciplines, creating researchers capable of addressing the multifaceted challenges of understanding planetary evolution. Only took the development of interplanetary analytical chemistry to realize that understanding ancient environments requires the patience of geological time combined with the precision of atomic scale measurement. The chemical archives preserved in these Martian formations will support scientific research for decades, their molecular secrets gradually yielding to analytical techniques that improve with each technological generation, ensuring that these ancient stones continue to reveal new information about planetary processes that operated when the solar system was young and Mars possessed the environmental complexity to support extensive geochemical cycles. The chemical parallels between ancient Martian evaporates and Earth's Archean-era formations reveal fundamental similarities in the geochemical processes that operated on both planets during their early histories, when thick atmospheres and abundant surface water created environments capable of supporting extensive hydrothermal systems and mineral precipitation sequences. Terrestrial formations from the Pilbara region of Western Australia and the Barberton Greenstone Belt of South Africa display mineral assemblages and trace element signatures that mirror those detected by Perseverance, suggesting that both worlds followed similar evolutionary pathways during their youth before diverging into their current dramatically different environmental states. Archean evaporite deposits on Earth formed under atmospheric conditions substantially different from modern terrestrial environments, with higher carbon dioxide concentrations and lower oxygen levels creating chemical conditions that more closely resembled those inferred for early Mars. The mineral assemblages preserved in these ancient terrestrial formations include many of the same sulfate and chloride phases detected in Martian deposits, though in different proportions that reflect the distinct atmospheric and crustal compositions of each planet. Isotopic signatures within Earth's oldest evaporite deposits provide reference frameworks for interpreting the Martian data, revealing both similarities and differences in the source materials and formation processes that operated on each world. Carbon isotope ratios in Archean carbonates suggest biological influence on atmospheric composition, while similar measurements in Martian samples show no clear evidence for biological carbon cycling. These isotopic differences highlight the divergent evolutionary pathways followed by the two planets despite their similar early environmental conditions. Trace element geochemistry of Archean hydrothermal systems reveals metal concentrations and distribution patterns that closely match those observed in Martian evaporite deposits, suggesting similar temperatures and chemical conditions during water-rock interaction. The rare earth element patterns and transition metal signatures indicate hydrothermal processes that operated under reducing conditions in both planetary environments. Though the specific redox conditions may have differed due to distinct atmospheric compositions and crustal oxidation states, sedimentological analysis of Earth's ancient evaporite sequences reveals depositional structures and layering patterns remarkably similar to those preserved in Martian formations, indicating that the physical processes controlling evaporite deposition operate according to universal principles regardless of planetary setting. The rhythmic bedding, crystal size variations, and mineral zonation patterns observed in both terrestrial and Martian deposits reflect similar hydrodynamic and chemical processes during brine concentration and mineral precipitation. The preservation potential of biosignatures in terrestrial Archean evaporites provides insights into the types of organic signatures that might be preserved in similar Martian environments if life ever existed on the red planet. Earth's ancient salt deposits contain preserved organic compounds, including possible microbial biomarkers that have survived billions of years of geological change. Only took the development of life on one planet to create preservation templates for searching for similar signatures on another world. Comparative studies of sulfur isotope systematics reveal fundamental differences in the sulfur cycles that operated on early Earth and Mars, despite similarities in many other geochemical processes. Terrestrial Archean sulfur shows mass-independent fractionation signatures attributed to atmospheric photochemistry under an oxygen-free atmosphere, while Martian sulfur isotope patterns suggest different atmospheric processes or sulfur sources that created distinct fractionation mechanisms. Paleo-environmental reconstructions based on mineral stability relationships indicate that both planets maintained surface temperatures above the freezing point of water during their early histories, though through different mechanisms. Earth's greenhouse warming relied primarily on atmospheric carbon dioxide and water vapor, while Mars may have required additional greenhouse gases or episodic warming mechanisms to maintain liquid water stability under the fainter solar luminosity of the early solar system. The irony of using Earth's most ancient rocks to understand Mars's geological history reflects the temporal scales over which planetary evolution operates, with processes that ended on Mars billions of years ago continuing to operate on Earth in modified forms. Earth's ongoing geological activity gradually destroys evidence of its earliest environmental conditions, while Mars preserves perfect archives of similar processes that operated when both planets possessed thick atmospheres and active hydrological cycles. Microbial ecology studies of modern terrestrial evaporite environments reveal diverse biological communities adapted to the high salinity conditions similar to those inferred for ancient Martian groundwater systems. These extremophile organisms demonstrate that life can persist and even thrive in chemical environments that would have been toxic to most familiar forms of life, expanding the range of conditions considered potentially habitable on other worlds. Geochemical modeling studies that successfully reproduce the observed mineral assemblages in terrestrial Archean deposits provide validated frameworks for interpreting similar formations on Mars. The thermodynamic models developed for Earth's ancient hydrothermal systems can be adapted to Martian conditions by adjusting for differences in atmospheric pressure, temperature, and crustal composition, creating predictive tools for understanding ancient Martian environmental conditions. There remains uncertainty about the relative timing of environmental transitions on Earth and Mars, as both planets experienced major atmospheric and climatic changes during the Archean Proterozoic transition period. The synchronization or independence of these evolutionary changes has implications for understanding the factors that control planetary habitability and the potential for life to develop on worlds with different evolutionary histories. Comparative planetology research programs increasingly focus on understanding the factors that caused Earth and Mars to diverge from similar early conditions into their current dramatically different environmental states. The preservation of ancient environmental records on Mars provides opportunities to study planetary processes that operated before Earth's geological record began, offering insights into the early evolution of terrestrial planets that would be impossible to obtain through study of Earth alone. Astrobiology research strategies increasingly rely on Earth-Mars comparisons to define the environmental conditions most likely to support the origin and early evolution of life. The chemical signatures preserved in ancient evaporate deposits from both planets provide constraints on water activity, nutrient availability, and energy sources that help define the boundaries of planetary habitability under different atmospheric and geological conditions. Sample return missions planned for both Mars and Earth's ancient terrains will enable unprecedented laboratory comparisons between planetary materials that formed under similar environmental conditions billions of years apart in space and time. These comparative studies will provide definitive tests of hypotheses about early planetary evolution and the factors that control the development of habitable environments on terrestrial planets. Only took 4 billion years of separate planetary evolution to create natural experiments in comparative environmental chemistry, with Earth and Mars serving as complementary laboratories for understanding the factors that control planetary habitability and atmospheric evolution. The ancient evaporate deposits preserved on both worlds represent archives of environmental conditions that existed when the solar system was young. Their chemical signatures providing windows into planetary processes that operated before life began its transformation of terrestrial surface environments through biological weathering and atmospheric modification. The precious samples now sealed within Perseverance's collection tubes represent some of the most carefully curated geological specimens in the history of planetary exploration, each fragment destined for a journey across the solar system that will span decades before sophisticated Earth-based laboratories can unlock their molecular secrets. The sample return architecture requires unprecedented coordination between multiple space agencies and engineering teams, creating technological systems capable of maintaining sample integrity across interplanetary distances while preserving the pristine chemical and isotopic signatures that hold keys to understanding ancient Martian environmental conditions. Mission planners envision a complex choreography of robotic operations that will unfold over the next decade, beginning with the arrival of a sample retrieval lander that will collect the cached tubes and transfer them to a Mars ascent vehicle capable of launching the precious cargo into Martian orbit. The engineering challenges of launching samples from Mars represent formidable obstacles that require solutions to problems ranging from dust contamination prevention to the precise orbital mechanics needed to intercept the ascending samples with a waiting orbiter. The Earth Return Orbiter will maintain the samples in controlled environments during the months-long journey back to Earth, protecting them from cosmic radiation and temperature fluctuations that might alter their chemical compositions. Specialized containment systems will preserve the samples under Mars-like atmospheric conditions, maintaining the integrity of volatile compounds and preventing contamination that could compromise the scientific value of these irreplaceable specimens. Only took 50 years of space exploration to develop the technology necessary to bring pieces of another planet home for detailed study. Laboratory facilities being designed specifically for Martian sample analysis represent the most sophisticated geological research environments ever constructed, with containment systems capable of preventing both forward and backward contamination while enabling analysis at the molecular level. These facilities will operate under biosafety protocols that assume the potential presence of Martian life forms, though the likelihood of viable organisms in these ancient samples remains extremely low based on current understanding of Mars's environmental history. The analytical capabilities that will be brought to bear on these samples exceed those of any previous geological investigation, with techniques including atom probe tomography, nanoscale secondary ion mass spectrometry, and synchrotron-based X-ray spectroscopy that can reveal chemical and isotopic information at unprecedented spatial resolution. These advanced analytical methods will enable scientists to examine individual mineral grains and even crystal defects that preserve information about formation conditions and subsequent alteration processes. International protocols governing the distribution and analysis of returned Martian samples ensure that these unique specimens will be available to researchers worldwide, creating opportunities for collaborative studies that transcend national boundaries and institutional affiliations. The sample allocation process balances the scientific value of proposed research with the irreplaceable nature of the materials, ensuring that each analysis contributes maximum scientific knowledge while preserving samples for future studies using techniques not yet developed. The irony of waiting decades to analyze samples that preserve information from billions of years ago reflects the temporal scales that govern both planetary evolution and human technological development. The chemical signatures locked within these crystalline archives have remained stable across geological eons. Yet accessing their secrets requires technological capabilities that humanity has only recently acquired through decades of scientific and engineering advancement. Comparative analysis protocols will enable direct laboratory comparisons between Martian samples and terrestrial materials that formed under similar conditions, providing definitive tests of hypotheses about early planetary evolution that can only be addressed through detailed examination of actual planetary materials. These comparative studies will reveal both the universal aspects of planetary geochemistry and the unique characteristics that distinguish different worlds. Contamination prevention measures throughout the sample return process require extraordinary attention to cleanliness protocols that exceed those used in the most sensitive terrestrial laboratory environments. Every surface that contacts the samples must be documented and characterized to enable identification of any terrestrial contamination that might be introduced during handling and analysis. The chain of custody documentation will provide complete records of sample handling from collection on Mars through final analysis on Earth. There remains uncertainty about the preservation of organic compounds and isotopic signatures during the extended storage and transport periods required for sample return. Laboratory studies of analog materials suggest that most mineral phases will remain stable during the return journey. Though some volatile compounds might be lost or altered, understanding these potential changes requires careful calibration studies using terrestrial materials subjected to similar storage and transport conditions. Advanced analytical techniques under development specifically for Martian sample analysis include new approaches to isotopic analysis that can detect smaller quantities of rare isotopes and provide higher precision measurements of isotopic ratios that carry information about ancient atmospheric conditions. These technological developments push the boundaries of analytical chemistry and will likely find applications in other fields requiring ultra-sensitive chemical analysis. The scientific questions that will be addressed through analysis of returned samples span multiple disciplines including geochemistry, astrobiology, atmospheric science, and planetary physics. Each discipline brings unique analytical approaches and interpretive frameworks that will contribute to comprehensive understanding of the environmental conditions recorded in these ancient formations. The interdisciplinary nature of the research requires collaboration between specialists who rarely work together on terrestrial problems. Educational and outreach opportunities created by the Sample Return Mission will inspire new generations of scientists and engineers while demonstrating the practical benefits of international cooperation in space exploration. The technological innovations developed for sample return will find applications in other fields, creating economic and societal benefits that extend far beyond the immediate scientific objectives of the mission. Quality assurance protocols ensure that the scientific conclusions drawn from returned sample analysis meet the highest standards of scientific rigor and reproducibility. Multiple laboratories will analyze aliquots of the same samples using different analytical techniques, providing independent verification of key results and ensuring that important discoveries can be confirmed through independent analysis. Archival storage systems will preserve portions of the returned samples for analysis by future generations of scientists equipped with analytical techniques not yet invented. The sample curation protocols recognize that these specimens represent irreplaceable scientific resources that will continue to yield new information as analytical capabilities continue to improve through technological advancement. Long-term research programs planned for the returned samples will continue for decades after their arrival on Earth, with sample analysis campaigns that build upon initial discoveries to address increasingly sophisticated questions about Martian environmental evolution. The samples will serve as permanent scientific resources that will support research efforts by multiple generations of planetary scientists. Only took the development of interplanetary sample return capabilities to realize that bringing pieces of other worlds to Earth represents one of the most challenging technological undertakings in human history, requiring coordination between engineering disciplines and international organizations on scales that rival the complexity of the planetary processes being studied. The blue-green crystals destined for this journey carry within their atomic structures information about environmental conditions that existed when the solar system was young, their molecular secrets awaiting revelation through analytical techniques that represent the pinnacle of human scientific and technological achievement. The discovery of these sapphire-hued formations represents a single thread in an increasingly complex tapestry of evidence, suggesting that Mars once possessed the fundamental chemical ingredients necessary for life to emerge and persist. Though whether biological processes ever actually operated on the red planet remains one of astrobiology's most compelling unsolved mysteries. The copper-bearing evaporite deposits join a growing catalog of Martian environments that exhibited conditions within the known tolerance ranges of terrestrial extremophile organisms, creating a picture of ancient Mars as a world where chemistry and physics align to create potentially habitable niches scattered across the planet's diverse geological landscapes. Orbital surveys conducted by multiple spacecraft over the past 2 decades have identified thousands of locations where similar mineral assemblages might be preserved, suggesting that the processes documented in this particular canyon operated across regional and possibly global scales during Mars's early history. The widespread distribution of clay minerals, sulfate deposits, and other hydrated phases indicates that water-rock interaction occurred throughout the Martian crust, creating an interconnected network of potentially habitable environments that persisted for millions of years. Comparative studies of extremophile organisms on Earth reveal metabolic pathways that could have operated under the chemical conditions preserved in these ancient Martian formations. Chemolithotrophic bacteria derive energy from the oxidation of sulfur compounds, iron minerals, and other reduced chemical species that were abundant in the Martian groundwater systems. These organisms demonstrate that life can thrive in environments characterized by high salinity, elevated metal concentrations, and limited organic carbon availability. The temperature constraints derived from mineral stability relationships suggest that the ancient Martian groundwater systems maintain conditions within the known temperature ranges for hyperthermophile organisms, which thrive at temperatures exceeding 80 degrees Celsius. These high-temperature environments might have provided thermal energy to drive complex organic chemistry while creating selective pressures that could have led to the evolution of robust biochemical systems capable of surviving in extreme environments. Nitrogen availability represents one of the key limiting factors for biological processes, and the search for nitrogen-bearing compounds in Martian samples continues to yield equivocal results. While some measurements suggest the presence of nitrate minerals that could have provided bioavailable nitrogen, the concentrations remain near the detection limits of current analytical techniques. The nitrogen inventory of ancient Mars represents a critical constraint on the planet's biological potential that requires further investigation. The preservation potential for biosignatures in evaporate environments has been demonstrated through studies of terrestrial salt deposits that contain molecular fossils and cellular structures preserved for hundreds of millions of years. These findings suggest that similar Martian formations could preserve evidence of ancient biological activity if it ever existed. Though detecting such signatures requires analytical techniques that approach the limits of current instrumental capabilities, only took 4 billion years for the search for life to focus on environments that would have been hostile to most familiar organisms, highlighting the expansion of scientific understanding about the environmental conditions that can support biological processes. The extreme chemical conditions recorded in these Martian formations would have challenged any potential life forms with high salinity, elevated metal concentrations, and fluctuating redox conditions that require specialized physiological adaptations. Phylogenetic studies of terrestrial extremophiles suggest that organisms capable of surviving in high salinity, metal-rich environments represent some of the deepest branches in the tree of life, implying that such capabilities may have evolved early in biological history. If life ever existed on Mars, it might have developed similar adaptations to cope with the challenging chemical conditions that characterize the planet's ancient groundwater systems. The energy budgets available to support biological processes in these ancient Martian environments can be calculated based on the chemical gradients and redox couples preserved in the mineral assemblages. These calculations suggest that sufficient chemical energy was available to support chemolithotrophic metabolism. Though the energy flux rates may have been lower than those typical of terrestrial hydrothermal systems due to the different atmospheric and thermal conditions on early Mars, organic geochemistry studies of the evaporate samples continue to push the boundaries of detection sensitivity in the search for carbon-based signatures that might indicate biological processes. While no definitive organic biomarkers have been identified, the analytical techniques continue to improve with each measurement, gradually approaching the sensitivity levels needed to detect the minute quantities of organic compounds that might be preserved in these ancient formations. There remains fundamental uncertainty about whether the environmental conditions that appear suitable for life from a chemical and physical perspective would have been accessible to biological colonization. The isolation of subsurface groundwater systems might have prevented biological dispersal even if life existed elsewhere on early Mars, creating chemical oases that remained sterile despite their apparent habitability. Astrobiology research strategies increasingly focus on understanding the relationship between habitability and the actual presence of life, recognizing that environments that possess the chemical and physical prerequisites for biology may nonetheless remain uninhabited due to historical contingencies, dispersal limitations, or the stochastic nature of life's origin. The distinction between habitable and inhabited environments represents one of the central challenges in astrobiology research. The search for biosignatures in returned Martian samples will require the development of new analytical approaches capable of distinguishing between biological or biological organic compounds in samples that have experienced billions of years of potential alteration. The chemical signatures of ancient life may be subtle and easily confused with abiotic processes that can produce similar molecular patterns through purely chemical mechanisms. International astrobiology research programs coordinate efforts to study terrestrial analog environments that might provide insights into the types of biosignatures most likely to be preserved under Martian conditions. These analog studies help define the analytical strategies and detection criteria needed to recognize evidence of ancient biological activity in samples from environments unlike any that exist on modern Earth. The temporal scales required for life to originate and establish stable ecosystems remain subjects of active research, with implications for understanding whether the duration of habitable conditions on early Mars was sufficient to support biological evolution. Laboratory studies of the origin of life suggest that the transition from chemistry to biology might require millions to tens of millions of years, though the specific environmental conditions that facilitate this transition remain poorly understood. Planetary protection protocols governing the search for life on Mars recognize both the scientific importance of preserving any indigenous Martian biology and the need to prevent contamination that could compromise the search for biosignatures. These protocols will continue to evolve as understanding of Martian environmental conditions improves and as human exploration of Mars becomes increasingly likely. Only took the development of interplanetary astrobiology to realize that the search for life elsewhere in the universe requires understanding the full range of environmental conditions that can support biological processes, pushing scientific inquiry into chemical and physical realms that challenge conventional definitions of habitability. The ancient Martian formations preserve windows into environments that existed when both Earth and Mars possessed the potential to support life. Their chemical archives waiting to reveal whether biology represents a universal response to suitable planetary conditions or a rare occurrence that distinguishes Earth as unique among the worlds of the solar system. Mars continues its ancient orbital dance through the cosmic darkness, carrying within its silent canyons and mineral-veined rocks the crystallized memories of rivers that once carved channels beneath skies heavy with water vapor and possibility. The planet moves with the same gravitational precision that governed its motion when these blue-green formations first precipitated from groundwater springs. Yet everything else has changed in ways that would render the ancient world unrecognizable to any observer familiar with the current rust-colored landscape of endless dust and thin atmosphere. The copper sulfate crystals embedded in canyon walls maintain their molecular arrangements with the patience that only geological time can teach, each atom locked in position by chemical bonds that have remained stable through billions of years of planetary evolution. Their crystalline lattices preserve information about water chemistry, atmospheric pressure, and thermal conditions that existed when the solar system was young, and Mars possessed the environmental complexity to support extensive geochemical cycles involving flowing liquids and atmospheric circulation patterns. Seasonal changes on modern Mars consist of subtle variations in atmospheric pressure and temperature that pale in comparison to the dramatic weather systems that once redistributed water across the planet's surface through precipitation cycles, river flooding, and evaporation processes that concentrated dissolved minerals in temporary lakes scattered across the ancient landscape. The planet's current meteorology operates within ranges that would have represented extreme drought conditions during its early hydrologically active period. The silence that fills these canyons carries no echo of the sounds that once reverberated through them when flowing water carved bedrock and transported sediments toward temporary seas that existed in impact basins and low-lying regions across the planet's northern hemisphere. The acoustic environment of ancient Mars included the murmur of running streams, the splash of water over stone barriers, and the gentle lapping of waves against shorelines that have since been buried beneath layers of dust accumulated over geological ages. Perseverance continues its methodical exploration of these geological archives, its instruments documenting mineral compositions and textural relationships that will be studied for decades as researchers gradually decode the environmental history preserved in crystalline form. The rover operates with mechanical persistence that mirrors the slow geological processes it investigates, each measurement adding incremental understanding to questions that span billions of years and interplanetary distances. The technological achievement represented by this robotic exploration reflects humanity's growing capability to extend scientific inquiry across the solar system, creating opportunities to study planetary processes that operated long before Earth developed the oxygen-rich atmosphere that supports complex life. Only took 50 years of space exploration to develop the instruments necessary to read chemical messages written in stone when the solar system was half its current age. Future missions will build upon these discoveries, targeting similar formations in other regions of Mars to determine whether the processes documented in this canyon represent local phenomena or evidence for planet-wide environmental conditions that characterize the early Martian climate system. The expansion of exploration to multiple sites will provide the regional context necessary to understand the global implications of these ancient hydrothermal and evaporative processes. The scientific legacy of these discoveries will extend far beyond Mars exploration, contributing to understanding of planetary evolution processes that operate throughout the solar system and beyond. The principles governing water-rock interaction, atmospheric evolution, and mineral preservation apply to exoplanets orbiting other stars, where similar processes may be creating or destroying habitable environments under conditions that can only be studied through the development of increasingly sophisticated telescopic observations. There remains something profound about finding evidence for ancient oceans preserved in desert stones on a world that no longer knows the luxury of liquid water at its surface. The evaporate deposits represent both endings and beginnings, the end of Mars's active hydrological period and the beginning of human understanding of planetary processes that operated when Earth was still forming its earliest continental crust. The cosmic perspective provided by these discoveries places Earth's environmental history in broader context, revealing both the fragility and resilience of planetary climate systems over geological timescales. Mars serves as a natural laboratory for studying atmospheric evolution and surface-atmosphere interactions under conditions different from those that shaped Earth's environmental development, providing insights into the factors that control planetary habitability. Educational opportunities created by Mars exploration inspire new generations of scientists and engineers while demonstrating the practical applications of fundamental research in physics, chemistry, and geology. The technological innovations developed for planetary exploration find applications in environmental monitoring, materials science, and other fields that benefit from advances in remote sensing and analytical instrumentation. The philosophical implications of discovering evidence for ancient habitability on Mars challenge conventional assumptions about the uniqueness of Earth's environmental conditions and the likelihood of life existing elsewhere in the universe. These findings suggest that habitable environments may be more common than previously thought, though the transition from habitability to actual biological activity remains one of science's greatest unsolved mysteries. International cooperation in Mars. Exploration demonstrates humanity's capacity for collaborative scientific endeavors that transcend national boundaries and political differences in pursuit of knowledge that benefits all of Earth's inhabitants. The shared excitement of discovery creates common ground for international dialogue and cooperation that extends beyond scientific research into broader areas of human interaction. Only took the exploration of a dead planet to reveal the dynamic history hidden within its silent landscapes, where flowing water once carved channels and deposited minerals under skies that knew clouds and weather systems operating according to the same physical principles that govern Earth's atmospheric circulation. The blue-green crystals wait with mineral patience in their canyon walls, indifferent to the passage of seasons and centuries, preserving their chemical messages for future generations of explorers equipped with increasingly sophisticated tools for reading the stories written in stone. The red planet sleeps beneath its dusty atmosphere, its surface sculpted by winds that carry only the finest particles across impact craters and volcanic plains, where ancient rivers once meandered toward vanished seas. In the deepest silence of space, Mars maintains its orbital rhythm around a star that has grown brighter since these formations crystallized, its increased luminosity arriving too late to restore the atmospheric conditions that once supported the planetary water cycle preserved in these geological archives.